Hi guys, in this video we're going to be taking a look at one of our other exponential models, and we're going to refer to this as our logistic growth model, and it's this fourth model that you see here. And so with respect to our logistic growth model, let's go ahead and read through this because it's kind of a really cool kind of model here that describes a lot of time, like say, spread of disease through a population. So it says some populations will at first demonstrate rapid growth followed by a declining rate of growth. One model for describing this type of growth pattern is the logistic curve given by this function here, where y is the population size and x is the time here. And so we want to make sure that we indicate this here, but we tend to look at our dependent variable here as some population size, okay? And we look at x as being our time. And you know, in terms of units of time, it doesn't have to be in years or minutes. It could be arbitrary, but there will be some unit of time at which, you know, we're saying there is some population size, okay? So we say y is our population size, x is our time. Let's take an example of, say, bacteria culture that is initially allowed to grow under ideal conditions, and then under less favorable conditions that inhibit growth. So a logistic growth curve is also sometimes referred to as a sigmoidal curve. And so what I want to do is I want to make sure, at the very least, that we kind of represent this graphically and take a look at what would this look like. And so what I'm going to do is I'm going to say that this is our y-axis here, certainly our y-axis, but we're going to refer to this as some population of something. And then this is our x-axis, but we say x is really indicative of time. And so what's happening over time? Well, let's imagine that we had a population of people here. Let's say that there are 5,000 people in some population here. That means that there are no more than 5,000 people, but at the same time, let's say one person comes down with the flu virus. Well, what's going to happen when one person gets the flu? Somebody else is going to get the flu. And what's going to happen when those two people have flu? You know, more people are going to get the flu. And so when you have a population, what happens is at first, your population that has a flu virus, say, grows really slowly at first, but because there are people to infect, it starts to speed up. And it infects more people and more people until what starts to happen is there are less people infected with the virus than are infected. Sorry, less people not infected with the virus than are infected with the virus. And so what happens is it still continues to affect more people, but it slows down. And so you get this curve that just kind of looks like this right here. And this is what we refer to as our sigmoid curve or logistic growth curve. But you can see that our initial population is being infected very rapidly, but we can infect more than people than there were in the population in the first place. So when we look at these logistic growth curves or sigmoid curves, these are often models that look like this right here. The good news is, typically what's going to happen is you're going to be hooked up with this model. Somebody's going to give you this model, but we're going to have to be able to navigate it and solve for unknowns in these particular types of instances. So let's take a look at this example that I give here. It says, on a college campus of 5,000 students, one student returns from vacation with a contagious and long-lasting flu virus. The spread of the virus is modeled by this function y as a function of t or x, where y is the total number of students infected after t days. So it says the college will cancel classes when 40 or more of the students are infected. So the two things we're going to try to figure out here are how many students are infected after 5 days, and how many days how many days until the college cancels classes here. And so let's go ahead and do this. This is our best habit we can form when it comes to looking at models. But we're going to make a table here and we're going to put in our variables. And so we say we have time and population, and it's given as this relationship right here. So what we want to do for at least the first part of this is say how many students are infected after 5 days. So in terms of how many students are infected, are we looking for y or are we looking for t? You know, it looks to me like we're given a time here, 5 days, and we're asked to find out what is y, how many students are infected. So what I'm going to do is I'm just going to go over here to my table. I'm going to say, well, okay, after 5 days, how many people are infected? The way this works is when you're given a model, we're going to go plug in the known and solve for the unknown. So for part A right here, let's go ahead and get this started. We say that we don't know y, so we have y equals, but we do know the time. So we're going to say 5,000 over, and this is quite an expression here. We have 1 plus 4,999 e to the negative 0.8, and we're taking that times, let's put this in red here, times 5. So one important thing is going to be just how we craft this expression in a calculator here. So what I'm going to try to do is I'm going to try to take my time. I'm going to say 5,000. Actually, maybe I won't take my time. Maybe we'll try this all in one fell swoop here. So we say divided by, now here's where we need parentheses. We're going to we're going to quantify everything in the denominator down here so that it divides by that entire quantity. We'll put a beginning parenthesis here. We have 1 plus 4 with 3 nines. This is e to the power of, and we have negative, let me get that negative in there, negative 0.8 times, in this case, a time of 5, in this case, days. Okay, so we have an end parenthesis. Now that's the end parenthesis for my exponent here, the negative 0.8 times 5, and I need another end parenthesis for everything in the denominator. So if I hit enter now, we see about 54.02-ish. I'm going to go ahead and put that then in this column, and I'm going to interpret my result here as meaning that after about 5 days, we're going to have about 54.02 students that have come down with this, say, long-lasting flu virus here. Okay, so you can see that in this particular instance, it was really easy to plug in for t and solve for y because y was already by itself. For this next part, part B, it says after how many days will the college cancel classes? Now I hope that you were paying attention here because this problem actually has an extra step here, and that is to recognize that this says in the problem, the college will cancel classes when 40% or more of the students are infected. Well, how many total students were there? There were 5,000. So the problem here is that not that we don't know how many students are supposed to be infected before they cancel classes, that's 40%. It's just that we're going to need to go find 40% of the total population. So for part B here, let me scroll down a little bit here. What we're going to have to do is we're going to have to settle on what is 40% of 5,000 or of the population. And the way this works is when you want a percentage of a number, we take that percentage as a decimal and we multiply it by the amount of the thing we're trying to find the percentage of. So let me get my calculator on here. I'm going to say I want 40% of 5,000. We're going to take that times 0.40. And so what we find out is it's 2,000 students. We say 2,000 here. But that just means that what I know is I want to find the time when 2,000 students are infected. And so one might surmise that, well, it's got to be more than 5 days because only 54-ish students were infected according to our model at 5 days. So then let's take our model here. We're going to say letter B. And this is going to involve a little bit more work because we're going to have to solve for t in this model. And that's what makes this an exponential equation that we have to go solve. So we're going to plug in for our y value here. We're going to say 2,000 students are infected of the initial 5,000. What would have to be the time in order for this to be the case? And so we're going to go ahead and put our model back together. E to the negative 0.8t. And the thing here is that we have to solve for t. So I'm going to give you guys lots of very good advice on how to solve a logistic growth model. And one piece of advice that I'm going to give you right off the bat is this. If you put your 2,000 over 1, we have 2,000 is to 1 is 5,000 is to this 1 plus 4,999 e to the negative 0.8t. And so what I want you to understand is that when you have two equal fractions like this, we refer to that as a proportion. And with proportion math, the neat thing is we can say that this is true if and only if their cross products are also equal. And so I want to show you that this is actually the case. You know, if I gave you an instance where I said, did you know that 1/4 is the same as 2/8? You say, well, of course it is. If I say, well, if you do their cross products also, though, you would discover that you would get the same balance on this diagonal as you would on this diagonal here. And so because that's the case, what we can say is that we can take 2,000 times everything in this denominator here. We're going to say is 2,000 times 1 plus 4,999 e to the negative 0.8t. And we're going to get the same thing as 5,000 times 1. Now, in order to solve for t, we've got to kind of get the base e by itself here. And so before we do that, we're actually going to divide both sides by this 2,000 that you see here. So we say 2,000. And what that does is it kind of sets us up on the left-hand side to go ahead and continue to solve for the base here, which is that e. We're going to isolate the base. On the right side, I get 5,000 over 2,000. I'm actually going to just go ahead and call that 5/2, and I'm going to leave that as an exact value where we're able to cancel out common factors of 10 here. So where did we end up? Well, looking at the initial problem here, and let's put this in a blue box. And then where I'm at now, what I want you to recognize is that really all that happened was the 2,000 here and everything in this denominator just sort of switched places. And that is just the result of if we were to do a cross product on each of these diagonals here, the next step would be, once I get this cross product on the left, is to divide by the 2,000, which really brings that 2,000 back over to underneath this 5,000 that was there on the numerator on the right-hand side. And then the 1 plus 4,999 e to the negative 0.8t actually goes up on the top left. So with logistic growth models, a really quick and easy way to remember this is you can always take the denominator on the right and the numerator on the left and switch those out. And that is to say that with proportions here, it's always fair to say that as long as you switch things on a diagonal, so like A and D switch places here, we would have D over B is the same as C over A. As long as you switched them on a diagonal, they're still equal. So now that I have these switched around, it's going to be a big isolation game now where we're trying to get E by itself. So let's go ahead and start with this. We need to subtract 1 from both sides, which I need a little bit of room here. We're going to say that leaves us with, on the left here, 4,999 e to the negative 0.8t, and that is equal to 5 halves minus 1. Now, we need to take all of this to isolate the base e and divide by 4,999. So you can see algebra is just wonderful when you have all sorts of different things going on here. But it's manageable. It means we can get through this. And so I'm actually going to write this as 5 halves minus 1 all over 4,999. So our next step here would be to proceed to go ahead and take the natural log of both sides. Now we want to use a log with the same base as our exponential expression on the left, and that's why we're using the natural log. But I'm going to wrap both these sides up. I'm going to say the natural log of the left must equal the natural log of the right, and because of our inverse properties, it allows us to say that what we're left with here on the left is just negative 8/10 t. On the right side we have all of this, the ln of 5 divided by 2 minus 1 all over 49.99, and the last thing we have to do here is divide both sides by negative 0.8. Okay, so what this should do is it should isolate our time for us. And I'm going to put a big box around this because I'm going to say that that really is our exact value on time. So the algebra set aside, I mean, the algebra was kind of the easy part. I think the hard part here is going to just be evaluating it on my calculator. So let's take our time here. I'm going to start with just this numerator right here, the ln of all this stuff. And so when I type in the ln, it already gives me a beginning parenthesis. But what I notice is I have an expression in this numerator over here that would need to be evaluated first before I could divide it by the 49.99. So when I type this in, I'm going to type in ln of, in parentheses, 5 divided by 2 minus 1, all of that divided by 4,999. Try that again. And then in my parenthesis, so we have the ln of this big expression here, and then all of that is being divided by negative 0.8. And so what this should do is give us about a number of days here, about 10.14. So 10.14, we want to make sure that we label this with units here, but this would be a time. And so it would only take about 10.14 days for the school or the college or whatever it is to cancel classes, because at that point 40% of the student body would be infected. So just know this, with our logistic growth curves, you're likely going to be given this model here, and just with any other model, we're going to be asked to find a time at which a certain number of students are, say, infected, or maybe find out how many students are infected at a given time, but have one known and go find the unknown.